And welcome back to another edition of Physical Geography 1114 online. Hopefully by now spring break's coming to an end and you're starting to look around and review some of these things that I posted on YouTube. Hopefully you're getting into some type of routine as far as getting learning this online class, how it's going to work. So anyway, we've adopted it and you're just going to have to bear with us, but hey, we're doing the best we can, right? Today's chapter 14, the internal processes. Hey, volcanism. Let's watch some stuff blow up, right? All right. And again, we're using the landscape appreciation, McKnight's Physical Geography, landscape appreciation that is put out by Pearson. All right. Again, hopefully now I have covered myself for plagiarism. All right. Today we're going to go over the internal processes. Now this again is just like all the other tutorials. It's a two-part tutorial. This is part one. Part two will follow up later. So we're going to start out from the rigid earth to plate tectonics, the theory of plate tectonics and volcanism. We'll start getting into volcanism, but that'll carry on into number two. All right. As well as folding, faulting, and the complexities of the internal processes. Example, the Northern Rockies. I love the Rockies. There's a lot of things that make you question how the Rockies are where they're at. All right, from the rigid earth to plate tectonics, continents seem fixed from a human perspective. People didn't believe the continents moved around. They thought, hey, they're just here. But no, we did some studies. Dr. Wegener, Alfred Wegener, who we will talk about here in a second, he's the first person that came up with continental drift or plate tectonics. And he's the one that surmised that at one time they all fit together and created Pangea and then broke apart one at a time and to where they are now and have moved into their fixed position where they're at now. And I shouldn't say fixed position, they're still moving. Until the mid-20th century, scientists believed Earth's continents were rigid. And then along came continental drift. And how did it work? Well, people started noticing geologic features. Hey, this continent has the same rock types as this, and this continent has the same type of formation as that. And it was backed up with fossil paleontology data. Hey, we find these species here, we find these species here, but we don't find them over here. Why is Australia different? Why is Madagascar different? So they started looking at it. It all comes down to when the continents broke away from the supercontinent of Pangea. So again, evidence includes similar geologic features on coasts of different continents, and if you cut them all out and paste them together, they pretty much fit together. Oh, there's a few gaps here and there, but basically they all fit together. So again, paleontology supports continental drift. Again, one continent or two or three, maybe all of them have the same species, and then all of them have all but one, or so on. And this comes back to what we were talking about in the last chapter. The first first arrival date, and the last arrival date. Okay, LAD and FAD. So, or first appearance, I should say. First appearance date, last appearance date. So anyway, this comes back to our gold spikes and where we take and do geologic time and everything else. Geology, paleontology, it all works together. Glaciation continents reconstructed and made sense. They kind of bound everything together. We go, okay, well, we got a gap here. Antarctica kind of fits in that gap. Again, rejected by most scientists at the time, and this was in the 1920s. So we're talking 100 years ago, folks. We're not talking, the Greeks or whatever. We're not talking thousands of years or the Egyptians. It's only been 100 years. All right. Some of you may have grandparents that are 100 years old. So back then, this would have been like fake media to them. This was fake news. Oh, they couldn't be moving around. Well, now it's accepted. We've learned a lot. And again, even up until the 1980s, I'm going to say I was back here when I first started school a long time ago. They were still questioning it then. There were still paleontologists and stuff saying, is this true? And it wasn't until they ran their magnetometers and stuff that they said, yeah, there's things moving around. Okay. So what's some of the evidence here? Plate boundaries. Earthquake occur along these lines. And these lines correspond with locations of trenches and ridges in the seafloor. So again, we get the seismic action under the water. Okay, we can't see it. That's why we question it, because we couldn't see it. But again, seismology, magnetometers, everything else, we started going, oh, wait a minute. The mid-Atlantic ridge is spreading apart, and we have subduction along the Pacific plate boundary. So seafloor spreading. This is an important one. So the Atlantic Ocean has a mid-Atlantic ridge. Mid-ocean ridge formed by magma rising up from the mantle. So we have magma coming up out of the crust. New basaltic ocean floor created moves away from the ridge, so it's spreading apart, which means if you're spreading the Atlantic apart, the Atlantic is more or less growing, which means you've got to have something somewhere else shrinking, which is why along the Pacific plate, we have a lot of subduction going on. And we have other ridges and stuff in other places, but if you have something spreading apart, you got to have something being shrunk up. Okay. At trenches, older lithosphere descends into the asthenosphere where it is recycled through subduction, and we're going to get more into subduction. But if we look at our figure here, 1418, you can see our fault boundaries here, our mid-ocean ridge, and we can see how the plate is being subducted under the continental plate. You got to remember, ocean plate is more dense, so it will always go under continental. Continental is more buoyant, so it rides up over the ocean plate. And there's that MOHO discontinuity, which right there, that's that boundary. All right, on to the next slide. Oh, so here's some of the evidence. Paleomagnetism. I've already mentioned this several times. Iron in the cooled magma orients itself with the magnetic pole. So again, as long as that hot magma is liquefied, those iron minerals, they can orient themselves. And because they're iron and they're attracted magnetically, they're going to line up with north and south. Okay. And when they ran that magnetometer across these ridges, they noticed that, guess what? They move around. They flip one side the other, and then sometimes they do a 180. Okay? It provides a record of the past magnetic fields. The magnetic field has changed orientation at least 170 times in Earth's history. That doesn't sound like a lot, but if you figure about every 100,000 years, and we've already talked about Milankovitch cycles, makes you question, when's the next polar reversal happening, right? Should be symmetry in magnetic orientation, and used to verify the age of the rocks on the ocean floor and sea floor spreading. Because we can tell when something changes and we kind of know what rate the spreading is happening at, we can determine age. All right, plate tectonic theory. Theory behind motion of lithospheric plates. The plates float on the asthenosphere. Again, with the MOHO discontinuity in between, okay? 7 major plates, 7 intermediate plates, and 12 smaller plates. Now, back when I was in school, way back when, there was only 7 major plates. That's all they knew about. So we have learned a lot about plate tectonics since then. Smaller plates are large plates that are being subducted. Driving plate tectonics, slow convection in the Earth's mantle. Remember, convection, warm down, warm up, cold down, so we get that cycle going, okay? Convection can push plates away from each other. Most motion results from plates pulled by subduction of the dense oceanic lithosphere. Again, it's being pulled down, it's being torqued under like so. And it's still an ongoing area of research. Now, real quick, when we're talking about that torquing down, we always hear about tsunamis and how they're associated with earthquakes. We'll talk about this again. But what it is that torquing, when you got that torquing, eventually something has to give. And when it does and it snaps, that's when you get the displacement of water. That water gets pulled in and then released. Okay? So here are our tectonic plate boundaries. Now, a lot of people like their own plate boundary. I've got to tell you right now, my favorite is the Nazca plate. That's all there is to it. It's associated with the Nazca lines in Peru. And if you get a chance, look up the Nazca lines in Peru. Google it, look at some of the images. These things are amazing. They're awesome. They were created by the Incas, and you can only see them from above, from an airplane. You can't see them from the ground. From the ground, they just look like rows of rocks that somebody kind of kicked into a pile. But these are intricate designs. So if you get a chance, check out the Nazca lines of Peru. Okay. So my personal favorite plate is the Nazca plate. Right. So anyway, you see all your plates here, all your other plates. I want you to look though right here, and we're going to talk about this later on when we're talking about the Rockies. But as you can see, we have plate subduction right here, and then we have the Nazca plate. And here we have the San Andreas Fault, and we have the Juan de Fuca. Now, from what they know, this is what they can see. But what did this area here look like originally? Was it one big plate that is broken up into smaller plates? How does that work? Maybe this is what helped create the Rockies. All right, because we know that we have subduction going on and that the Andes Mountains are volcanic. Okay, here's your Andes Mountains. They are volcanic. And that's due to this subduction line right here. But what happens when this other plate, this Pacific plate and the Nazca plate, what happens, because we see the arrow here, it's pointing that direction, subduction. What happens when this plate completely gets subducted and the Pacific plate is then rammed into that coastline? I suggest that's kind of how the Rockies were created. A possibility, a hypothesis, if you might. That then the Andes, like the Rockies, would become dormant. They would be no longer volcanic. And just like the Rockies, which are here, and the Cascades, which are here, similar type of thing, the Cascades are volcanic. So is it possible that shut off that volcanism from the Rockies? We know there was volcanic activity at the Rockies, and we'll get into that a little bit later, right? But again, this is just my hypothesis. Hasn't been proved. I don't have the equipment to go out, and hopefully somebody else has written several papers on it. I don't know. Haven't looked it up. All right, so major plate boundaries. Here we go. First of all, we got transform plate boundaries right here. That's where they slide back and forth past each other, okay? We have the mid-ocean divergent plate boundary right here. That is seafloor spreading, okay? Seafloor spreading. And then we have our convergent plate boundaries. Now, there's one convergent plate missing here. First of all, we have ocean to ocean, ocean to continent, and we have continent to continent. Okay, so there's three different convergent plate boundaries. Convergent continent to continent created the Himalayas. The Himalayas are not volcanic, although they do see earthquakes, and that's because they've been slammed together. Okay, you got fracturing, you got folding, the whole works. Okay, remember, ocean plate subducts beneath continent plate. Okay, one ocean plate will subduct beneath another ocean plate, but you still got ocean to ocean. But when it's two continents, boom, both of them are going to explode up, okay? Now, anytime you have ocean plate involved in convergent plate boundaries, you will have volcanoes, okay? They are correlated together. Ocean plate, subduction, volcanoes. All right, so here's my divergent plate boundary. Plates move away from each other. This asthenosphere wells up in the plate opening, and it's represented by a mid-ocean ridge. Again, all these little lines here, boom, boom, you can see they're pulling apart. There's our spreading, and all these, that's what the magnetrometer runs across. Okay, we have all these little ridges. Associated with shallow focus earthquakes, and that's because you have the splitting, but you still have some transform plate boundaries that move back and forth past each other. Shallow focus earthquakes and volcanic activity because magma is coming up, so it is considered volcanism. This is considered constructive because it's building land, okay? It's spreading, it's building. And these can build a continental rift valley or what we call a proto-ocean. So again, it's building, it's expanding. All right, convergent plate boundaries, collision between plates. This is considered destructive, and depends on your terminology. What do I mean by destructive? Well, yeah, it's destroying the plates because they're disappearing. So you have destruction from a plate disappearing, but you are also building mountains. So, play on words. Again, there's three primary collisions, oceanic to continental. Oceanic plate sinks more dense, subduction. Forms an oceanic trench or continental mountains, e.g. Oh, wait a minute, what? The Cascades and the Andes. Oh, wait a minute. You mean to tell me my hypothesis might have a little bit of credibility here? And again, ocean, volcanic formation along the plates of continental volcanic arc. A lot of times we see forms of metamorphic rocks here, blue schist. Okay. Ocean to ocean, subduction results in an undersea trench. Now these trenches, again, that's where you have your deepest areas, right? The Marianas Trench, one of the deepest points in the earth as far as we know. There's not to say where there's one that we haven't found. We have deep and shallow earthquakes and island volcanic arcs. Oh, wait a minute. What did I just say? That's right. If you got ocean plate involved, then you have volcanism. And the last one, but not least, is continental to continental. No subduction, since two plates are highly buoyant, builds huge mountain ranges, the Himalayas, Mount Everest. Volcanoes are rare. I don't know that the Himalayas have one. I could be wrong. That's something for you to Google. There you go. Shallow earthquakes are relatively common, and again, that's because you got that pressure, both of them pushing up. And then we have our transform boundaries. Again, this is the two plates sliding past, faulting more or less. Two boundaries slip past each other laterally, transform faults. Neither creates nor destroys crust. It's just sliding, one past the other one, okay? Just sliding past. Commonly produce shallow focus earthquakes, such as the San Andreas Fault. Although the San Andreas Fault is a very large fault. Now, does this mean California is going to fall off into the ocean? Probably not. But that's not to say some volcanoes can't go off and help it out. All right, so around 450 million years ago, one supercontinent existed, and that was Pangaea. And then around 200 million years ago, it broke up, and we got Laurasia and Gondwanaland, right? And then the arrangement broke up some more into the current continental configuration. The Pacific Ring of Fire. Plate boundary exists all around the Pacific Rim. Look at this. The Ring of Fire. Okay, look at these. All these are volcanoes. Okay, all these are volcanoes. Boom. I actually almost looped those. 75% of all the volcanoes lie in the Ring of Fire. So what they say when we watch the Yellowstone videos, there's like 1,900 volcanoes. So you got to figure, what, 1,700 of them or so are right around this area. Highly volcanic. All right, so in addition to the basic plate tectonic theory is the mantle plumes or hot spots like Yellowstone. This is not due to subduction. This is a mantle plume. It's deep in the earth right here, and it's magma, and the magma makes its way to the surface. And so the continent moves, but the magma plume does not. Okay, so the magma plume stays where it's at, and the continent is what's moving. Whereas subduction, you have plates actually moving around. Okay, move with plates, so eventually become inactive, like the Hawaiian Islands. Okay, now if you look up, wait a minute, what is this? I can't see these dates real good, but it looks like 5.1, 2.6, 1.8. Wait, everybody, what's that? About 1.8 million last time. And if you look right now, we are actually, or not, I shouldn't say we, but another island, Lohi, I believe it's called, is being created now off of the coast. All right, so accreted terrains. What's an accreted terrain? Well, again, this could play into that whole Rocky Mountain Andes thing I've got going on. You have an old island arc system here, right? Okay, there's an old island arc from an ocean to ocean subduction. And eventually, that makes its way to the continent, just like I was talking about. And as you see, once it makes it to the continent, okay, boom, this gets shut off and the new one begins to build, okay? So accreted terrains. You might want to remember this. I think you probably see it again. All right, so questions. Mid-ocean mountain range formation, e.g. Appalachians. I don't know about the Appalachians. I've never studied the Appalachians, but I'm thinking possibly a small continent-to-continent type thing, okay? The number of plates and plate sizes have changed over Earth's history. Like I said, back in the day when I first started school, there were 7. That was it. 7 of them. Okay? Why are the earthquakes in the middle of the continent plates? Well, that's because of folding and faulting. Again, you got the mid-ocean ridge spreading apart. You got subduction over on the Pacific. So these plates are still moving around. Well, one plate may move a little faster than another. And so when you have that, you're going to have earthquakes. Why are plates different sizes? It all depends on subduction. First of all, we can only guess. Maybe it was the meteorite that took out the dinosaurs. We don't know. But something hit the Earth and maybe cracked it and got everything moving. It's possible it could have been like that from the get-go. I don't know. We don't have a time machine. If I did, I would love to go back and find out, hey, what got everything moving in this formation? And then why do plates form where they do? They really don't form. We're making more plate in the Atlantic, but it's not like the plates are really forming more, okay? They're more or less being subducted. All right, so definition of all phenomena connected to the origin and movement of molten rock. That's volcanism. You need to know this. So volcanism. Definition, all phenomena connected to the origin and movement of molten rock. Extrusive. Now, we've already went over some of this in the last chapter. Extrusive occurs on the Earth's surface. Just remember, extrusive, outside. Intrusive, within the Earth, okay? Intrusive volcanism occurs below the surface. Plutonic activity. All right. Magma versus lava. We already went over this. Magma within, lava on the outside. Okay. Magma is in a magma chamber. We can't see it. Once it boils out, it becomes lava. Violent or gentle eruptions. That depends on the amount of silicon that's in the magma. And we'll get into it here in a minute. And then pyroclastic material, these are the bombs when the big composite shields go off, composite volcanoes go off, kaboom. These are the bombs and stuff that start getting spit out and thrown all over the place. And then some self-destruct, such as Krakatoa in 1883. Tambora, we've seen the Yellowstone video, Yellowstone has went off several times. So Mount Pinatubo, I was in Clark Air Base about 6 months before it erupted. Mount St. Helens. Right? And just so you know, I've mentioned this before, but yes, we can tell some volcanoes are volcanic because they got steam vents and what have you. You see steam, but if there's no steam or none, a volcano looks just like any other mountain. It doesn't have a crater on it until it explodes. That's when the crater is created. All right, so here's our magma chemistry and styles of eruption. Now, we've talked about global warming. The big kaboom, spitting all that stuff into the stratosphere, blocking out the sun, leads to cooling. Could lead to an ice age if we got enough of it up there. But the one that erupts out kind of slow like Hawaii, that leads to global warming. Why? Because all that stuff is going into the ocean, heating the ocean up. So here we go. Nature of eruptions determined by magma chemistry, also by confining pressure. Is it getting spit into the stratosphere or is it just boiling into the ocean? Okay. Quantity of the silica in the magma is critical. High silica magma, all right, felsic magma, you get granite. Intermediate silica, you get andesite, magma, diorite. And low silica, magma, basalt, mafic magma, and basalt. So high silica eruptions have pyroclastics, okay? High silica. So the more silica you got, the bigger the boom. The low silica eruptions, quiet, non-explosive. This is the Hawaiian Islands, okay? Just kind of blows. Oh, you got a few pyroclastics maybe shooting out stuff, but for the most part, it's just kind of boiling into the water. Intermediate, some combination of the two. This could also, we could say Hawaii too, because Hawaii has always been kind of boiling around, but a couple of years ago, it kind of got a little out of hand. It decided it wanted to throw out some bombs. Now it's quieting back down. The fissures have quieted it back down. And so it's not going all crazy. Now it's back to being kind of a low silica. So maybe there was an influx or something. I don't know. I'm not a volcanism person, so that you would have to research. Volcanic activity, relatively temporary features on the landscape, and that's because they go boom or they move. Subduction changes. There's a whole bunch of things that change whether a volcano is a volcano and when it is active or dormant. Much of the Earth's water originated from water vapor from volcanic eruptions. You got to remember, when these things erupt and spit all that material in the stratosphere, you're talking sulfur, you're talking carbon, you're talking everything, water vapor. They talk about carbon dioxide from cars. Yes, cars put carbon dioxide, but so do volcanoes. So if everybody quit driving, great. Maybe we save the world. And then again, maybe 1,900 volcanoes go off and we go, a lot of good that did. Okay. Magma contains major elements required for plant growth. Lots of nitrogen and stuff in there too. And it provides soil fertility. But not right at first. The lava has to break down. You got to remember, it's hard, it's crusty. You can see here in this picture right here, yeah, there's some plant growth right here because it found a crack. And there was some moisture and some seeds got in there and made their way up. But it's got to break down, and it takes time. Once it takes time, it will put nitrogen and what have you into the soil and fertilize the soil and make it better for growing. Lava flows, column or basalt. Lava generally flows horizontal parallel to the surface along which it flows. If you've ever been to Yellowstone, some of you have, and this is when we were in class, I'd be like, hey class, who's been to Yellowstone again? And some of you'd raise your hand. And if you drive along some of those roads around Yellowstone or going to Yellowstone, you will see this type of formation. This is column or basalt. And some of the deposits around the Yellowstone area or on your way to it are quite thick. I'm talking several feet thick. I'm talking like 40, 50 feet thick. Okay, so you find some really big formations. It eventually cools in horizontal orientation strata. So eventually it's going to cool off. And a lot of this is because it's aligning itself. Streams following through lava flows result in irregular or fragmented surfaces. Uniform cooling results in hexagonal structure. We also have what we call flood basalts, most extensive of the lava flows. This is when you basically have those big supervolcanoes, okay? Flood basalt is a vast accumulation of lava buildup, and it correlates with mass extinctions. Mass extinctions. How many times did we see that Yellowstone went off? They told us about 3, but what did they say? There was, what, 17 other ones? So, again, this goes back to our golden spikes and correlations between extinctions and catastrophes. So now you start seeing how everything in Earth's history starts kind of playing a part, okay? This here's the last slide for today. This is volcanism. It tells you the different types of volcanoes. First of all, I want to just point out the composite volcano or the stratovolcano, that's the big one. That's the big Andes Mountain ones. That's the big ones that go kaboom, okay? There's a little bit smaller ones are the shield, broadly gently, mountain much broader than height and varies greatly. And then we have lava domes and cinder cones. Loose pyroclastic here, layers are solidified. I actually should take that back. I made a mistake there. Your composite, your big one, and your cinder cone is its baby brother. Okay. The shield and the lava domes, those are the low silica ones for the most part that just kind of bubble around. Okay. For instance, the Hawaiian Islands there for the shield, and you can see all these big ones here. So anyway, that's it for today. Hopefully you enjoyed this tutorial. We'll see you on the other side for part 2.